Hi, I'm going to tell you a little bit about how the Sandbox AQ Scholarship that I received this year has helped me in my research and what exactly I've been looking at since I received the scholarship last year. Well, I work in the context of distributed quantum computing, which is basically the setting where you have multiple quantum computers that are collaborating with each other in order to complete a computation that is larger than their individual capacities. In order to do this, they communicate through quantum networks, and they can be, in the same room or really, really far apart. But the main idea is that they're independent devices that are working together to complete this task. Now, in order to do that, you kind of have to bring together two fields within quantum technologies, quantum computing and quantum networks, and try to study how their interactions will look like in the future when we have, fully set up architectures and things like the quantum internet. The reason why we are even looking at this as researchers is because quantum computers are going to need a lot of qubits in order to, do these big computations that we believe are going to change the way we compute today. Applications will require thousands, if not millions, of qubits, and error correction, which will be necessary, is incredibly qubit hungry. So we know that we're going to need a lot of qubits to complete computations, and we know that our computations are going to look a little bit like this. It's going to be, this huge circuit or this huge set of instructions that will be, very difficult to come through because it will be so large. That is already happening in classical computers. I mean, very few people are out there working with, the source code, the actual, binary code that our computers are working in, just because it's so large, right? It's not human readable. And what we want to do in the setting of distributed quantum computing is take these huge quantum computations and basically map them to a network of quantum devices. But how to do this mapping, how to bridge this gap between the set of instructions that has been created and the problem that these computers need to solve, to what exactly do we tell each computer to do individually so they can together solve the problem, is, a question. The way researchers are looking at this problem now is through the lens of hypergraph partitioning. The hypergraph partitioning problem is this problem where you've got a hypergraph. So a hypergraph is very similar to a graph. The difference is that the nodes, so the vertices, they are not having two-way relationships. So there's not a connection between two vertices, but there might be a connection between three vertices. They're groupings. You have these groupings of vertices, and you might have a vertex that is in multiple groups at once. And basically, that's the difference. It kind of has like an extra dimensionality in a sense. And the idea of the problem is that you want to minimize the amount of these groups that you cut through whilst creating partitions that are balanced, meaning that for four players, so imagine four quantum computers, they are going to be assigned equally or roughly the same amount of nodes. These nodes can be, for instance, qubits, or they can be gates, the same amount of work. Now, in order to, do this jump, what we do is we take a huge computation, we map it to a hypergraph, which can be directed because most quantum computations have directed instructions, meaning you have a starting point and you have an ending point. Then you partition this hypergraph, you then map it to the devices, meaning you say, well, this part is going to go, this partition is going to go to this device, this partition is going to go to this other device. And then you basically have your mapping to your network of quantum devices. There's a few extra constraints that don't exist in the original hypergraph partitioning problem. So for a start, when you cut through your hypergraph, what you're basically creating is non-local operations that will have to happen between various devices. And that will require communication, and that communication can be different depending on the primitive that you use. You also have things like you can't really assign more qubits than would fit into your device because you don't have them, right? You cannot create a partition that has 10 qubits and send it to an 8-qubit device. So the way I am looking at this problem, looking at this field, is through a variety of pillars that I'm going to walk you through. The first one is basically looking at this first part of the problem where you have a huge computation and you want to map it to a directed hypergraph. You actually have various options on how to do this. As I said before, you can say your nodes are qubits. You can say your nodes are computational steps, meaning multi-qubit gates. And what I've been really interested in during my first year of PhD has been kind of exploring how we transform multiple types of computations. So not just circuits, but things like measurement-based patterns, quantum walks, all these different models that exist in quantum computing. How do we map them to a consistent abstraction? How do we do this equally for all these models? So this work is currently going through peer review. And then from there, it kind of evolved into exploring, well, sure, we have this problem that we're kind of saying is a simplification of our problem, but we're not really talking about the real, elephant in the room. What are we actually fully trying to solve? For instance, having balanced partitions is not actually necessary in our setting, but making sure we don't assign too many qubits to a device that doesn't have them is. So clearly defining, the mathematical problem that we're trying to solve is another piece of work that's been, kind of partially sponsored by this scholarship that I've been working on, and it's also currently in peer review. An additional pillar that I've been looking at a bit more recently has been noise, and how, the biggest issue in quantum computing right now is noise. The reason why we're not, already creating massive devices is because it's really hard to get a grasp to noise, and there's the entire field of error correction that's been trying to, solve this problem. And in a distributed setting, we have two sources of noise. We have the computers and the networks that have different types of noise and that need to, collaborate with each other. So how this noise is going to affect the distributed world is a very interesting and underexplored question. The first work that came out of my exploration has been this paper on how a specific, very well-known error mitigation technique looks in a distributed setting. It'll be presented at Infocom later this year. And then I've been able to develop an ongoing collaboration with researchers from an institution and other institutions on exploring how, error correction and noise will play a role in distributed quantum computing and what we can do about it. Beyond these pillars, I've been starting to build infrastructure. I've been starting to build software, open source software, like the HDH library, where I've been, putting out a lot of the work out there so other researchers can use it and, reuse the same code so that we have the same baselines when we're comparing things against each other. And that's been, really rewarding thing to do and to be able to be supported through. And yeah, finally, I just want to say thank you so much. I've really enjoyed the scholarship and the support. It's allowed me to, speak with experts around the world about the problems I've been working in and do my job more nicely. So thank you so much.